So for today's video, I wanted to do an example of conservation of angular momentum. This is a problem from the back of your chapter, but it has an interesting result that I want you to think about. So the scenario is that we have a uniform rod that is rotating in a horizontal plane. So it's rotating about an axis through its center. So this might sound familiar. You might be thinking, oh yes, I know. A rod with an axis through its center has a moment of inertia of 1/12 its mass times its length squared. This is true. Anyway, so we're given the mass of the rod and the length of it. Now, what we have though, in addition to that rod, is there's two small beads that are on the rod. There are catches on the rod that kind of act to keep the beads where they are. So initially when we're starting, the beads are 10 centimeters from the axis of rotation. The angular rotation rate, the angular velocity of the rod with the beads at that moment is 10 radians per second. Now what's going to happen next is the catches are going to release that are holding the beads, and the beads are going to slide to the ends of the rod. When that happens, we want to find the new rotation rate. So that's represented in this picture. Sorry that my rod came out so fat there, but it's the same rod as up here. Okay, so we want to find that new rotation rate, and we'll do that in a minute. But then in the end result, like the next part of the question asks, what will happen to the rotation rate if the beads fly off the ends and then they're not attached to the rod anymore? What will be the rotation rate then? And that's where I think you might find the result sort of interesting. I did a little work ahead of time, so to save us some time, I found the moment of inertia of the rod when it rotates about the axis in its center. That is not going to change. It's 1.67 times 10 to the minus 2. The units of moment of inertia are kilograms meters squared. Now, initially when the rods are 10 centimeters from the axis, the beads are going to add a moment of inertia. Each one would have a moment of inertia of mr squared. We have two beads, so the total moment of inertia to the two beads is twice the mass times the radius where they are squared. And that ends up to be 4 times 10 to the minus 4, and that of course is also kilograms meters squared. If we add those two together, because the total moment of inertia initially is that due to the rod with the beads where they are, that's going to be 1.71 times 10 to the minus 2 kilogram meters squared. Now, the next thing we want to look at is what's going to happen if the beads move to 50 centimeters. And let's just sort of look at that contribution before we start doing any more calculations. So if we think of that as the moment of inertia of the masses, and I'll say that's in case 2, would be twice the mass of the beads times the new radius squared, which would be 2 times their mass. 20 grams is 0.02 kilograms, and then they're going to be 0.5 meters away from the axis. And that changes their contribution to the moment of inertia to 1 times 10 to the minus 2 kilograms meters squared, which means that the total moment of inertia in that second situation is going to be 2.67 times 10 to the minus 2 kilograms meters squared. Okay, so I'm going to move aside so you can see those numbers. So the idea in this case is we're using the conservation of angular momentum. You should have an expectation as what's going to happen. Obviously, we see from our numbers that our moment of inertia is increasing as the beads move outward. We would have expected that anyway because there's mass further away from the axis of rotation. So we know the angular velocity is going to decrease, but let's see how much. So we're using the conservation of angular momentum. So I initial times omega initial is equal to I2 times omega 2. Omega 2 is going to be equal to the total angular momentum divided by the new moment of inertia. So that's going to be 1.71 times 10 to the minus 2 times 10 radians per second divided by 2.67 times 10 to the minus 2. And we get a new rotation rate of 6.4 radians per second. Again, just move aside so that you can see that. So it's 6.4. Maybe I'll get rid of the pink pen. It doesn't seem to be working as well. Okay, so that's how fast it's rotating now. And then we're going to ask ourselves, what is going to happen when the beads fly off of the ends of the rods? Now, initially, if we hadn't been trained in physics, we might imagine them just flying out like this. But we know better, because we know that at the instant that they were disconnected from the rod, they were moving with a velocity tangent to the circular path that they were in at the end of the rod. So they're actually going to move off. If you look right here, one bead will move off this way, one bead will move off that way. So, and they'll be going with that velocity. The velocity that they move with at that time is going to be equal to the angular velocity they had at that moment times the radius, which is the 0.5 meters. So we might want to think about the angular momentum of the beads at that instant from more of the traditional definition of angular momentum, which would be the radius crossed with the momentum. Now the radius and the momentum would be perpendicular to each other, so the angular momentum of the beads would just be simply the 0.5 times the angular velocity times the mass. So we're going to say that the angular momentum of the beads when they move off, there's two of them, times their mass, times their angular velocity times their radius, because this is their velocity, and then times another radius. So keep in mind that's just the mass times the velocity, which is the momentum, times the radius. But we've written their velocity as omega times r, where this is the omega 2, because the instant that they leave, the rod is rotating with that rate. So if we find that, their angular momentum is 6.4 times 10 to the minus 2. All right, so what is going to be the angular momentum or the angular rotation of the rod, given that that's what's happening? So I need to make a, sorry, I have duck off there. I need a little more room, so I'm going to erase this. And let's think about using conservation of angular momentum. And so we'll have the I2 times omega 2, which is what we had just been working with. Then the angular momentum of the beads plus the moment of inertia of the rod times what that omega is going to be. This is the omega, so I'll call this omega 3. That's what I'm actually trying to figure out. Notice I'm still using conservation of angular momentum, but I've written the angular momentum of the beads in this way. Because of the way they're moving, it makes more sense to me. And then the moment of inertia of the rod, of course. So it's still the beads plus the rod, which was what we used here for I2, was the beads plus the rod. It just had a different value. So this is, if I want to rearrange this, it would be I2 omega 2 minus the angular momentum of the beads divided by the moment of inertia of the rod would be omega 3. So I'd have 2.67 times 10 to the minus 2 times 6.4 minus 6.4 times 10 to the minus 2 divided by the moment of inertia of the rod, which is 1.67 times 10 to the minus 2. Does anyone have a prediction what that omega is going to be? You might be surprised when you get the answer, because the answer is 6.4 radians per second. It doesn't change. So I think that there's an instinct to believe that the rod will speed up or slow down because it's lost the moment of inertia of the beads. So if we think about that, if the beads are gone, it has less inertia, so maybe it'll speed up. But it's not the fact, because as I sort of alluded to in my conservation of angular momentum, the beads are still part of the system, and we still want to work with their angular momentum. They still contribute. And so in a sense, and what happens is their contribution, you could check it on your own, is actually exactly the same as it was when they were at the ends of the rods. It's exactly the same expression, because even if we look here, oh, it's like a mr squared times omega. It's exactly the same. And so the rotation rate of the rod doesn't even change. Surprising? Maybe. But hopefully it makes sense once you see it. All right, I'll see you tomorrow.